All right, so in this section, we're starting to talk about probability. And we're going to start by talking about just how to calculate the probability and what does it mean. So we'll start with some definitions. So any action in which the result is uncertain is called an experiment. So that might be something like rolling a die. Right, I roll the die. I don't know what I'm going to get when I roll it. Right, so there's some kind of an uncertainty to my experiment. The possible results of experiments, I should just say, of an experiment are called outcomes, and the set of all possible outcomes is a sample space. So if I roll a die, right, my sample space, what are my outcomes? I could roll a 1, a 2, a 3, a 4, a 5, or a 6. And we'll call that sample space S. Assuming, of course, that this is a 6-sided die, right? If I had a 20-sided die, my outcomes go all the way up to 20. Any collection of outcomes in a sample space is called an event. So maybe my event, and I'll call it E, might be rolling a 2. Or my event could be rolling, I don't know, rolling an even number. All right, so there are a lot of different events we can consider within our sample space that are possible results or outcomes from our experiment, rolling a die. So to define this, to define what probability really is, I can say for some event E in a sample space S, just so I can abbreviate a little bit, the probability of E, the event happening, is going to be written this way. We're going to use P of E, the probability of E happening. And we'll write it this way. We'll say it's the number of outcomes that satisfy E, the number of ways that the event can happen, divided by or out of the number of outcomes in S, the number of total outcomes that I could possibly have in my sample space. And of course, because this is a fraction and we're counting things, then my probability has to be somewhere between 0 and 1, right? And if my probability is 0, then we call this event impossible, right? So if I have my 6-sided die, I couldn't possibly roll a 7 with one single die. That's impossible. And if I have a probability of 1, then we say that my probability, my event is certain, right? It's definitely going to happen. If I roll a 6-sided die and I say I want to get a number between and including 1 and 6, I'm definitely going to get a number between 1 and 6 on my normal 6-sided die. So here's how this is going to look. What is the probability of rolling a 3 on a fair 6-sided die? So now it's important to note that fair here just means that all outcomes are equally likely. All right, so my die is fair because I could get a 1 just as easily as I could get a 4, just as easily as I could get a 6. All right, so my probability of rolling a 3, well, how many different ways can I satisfy that? There's only one way I can roll a 3, and that's to actually roll a 3. So if there's one way I can satisfy my event. But how many total outcomes are there? There are 6, right? If I roll one die, I could roll a 1, a 2, a 3, a 4, a 5, or a 6. So 1 out of 6. Sometimes you'll also see us express this as a decimal. So 1 out of 6, or 0.167. I like to go out to 3 decimal places just for the sake of security and just for the sake of rounding, right? I think sometimes going out just 2 is not enough. 4 seems excessive. 3 feels like a sweet spot. Okay, so kind of a simple example. Let's try another one. What's the probability of drawing a 5 of any suit in a standard 52 card deck? So of course, just as a refresher, we know that there are 4 suits. Right, we have 2 red suits. We have hearts. I might also use an H4. We have diamonds, which you might also see me use a D4. We have spades. That was terrible, which I'm going to use an S4. We have clubs, which was even more terrible of a drawing, which I'm going to use a C4. We have 2 red suits, 2 black suits, 4 suits in total. So my probability of drawing a 5 of any suit, well, how can I do this? Well, there are 4 5s, right? There's a 5 of hearts and a 5 of diamonds and a 5 of spades and a 5 of clubs. So there are 4 5s out of 52 cards total. So if I wanted to leave it as a fraction, I could reduce this, but I'm not gonna. I want the decimal. So there's a 0.077 approximately. Use my good notation here. Approximately chance of drawing a 5, right? And of course we can convert these to percentages, which is maybe how you're more used to seeing it. So we would say there's a 7.7% chance of drawing a 5. There's a 16.7% chance of rolling a 3. Right? We're much better at conceptualizing percentages out of 100 than proportions as decimals out of 1. So sometimes it's nice to convert to a percentage like that instead. Of course, we can go bigger. We can think even bigger because we've learned about permutations and combinations and all that stuff. So let's put this into practice with some real games here, right? So in poker, a royal flush is defined as having 5 cards, the highest 5 cards of rank in the hand. So that'd be the 10, the jack, the queen, the king, and the ace of one suit. And we can actually highlight that entire thing. If one suit of the same suit would be implied in a hand. So suppose you have a deck of cards, you deal 5 cards off the top of the deck. Out of your standard 52 card playing deck, what is the probability that you're dealt a royal flush? So we're going to look at it this way, and I'll show you a different way to maybe look at it later. But the way we're going to look at it is this. The probability of a royal flush is, well, the number of royal flushes that there are. So let's think about that. I could have the 10 of clubs and the jack of clubs and the queen of clubs and the king of clubs and the ace of clubs. I could do this with spades. I could do this with hearts. Ace of hearts. And I could do this with diamonds. Right? 10 of diamonds, jack of diamonds, queen of diamonds, king of diamonds, ace of diamonds. So there are 4 possible royal flushes. Now, how many possible 5-card hands are there? Well, this would be a combination, right? The order in which that they sit in my hand is irrelevant. It just matters that they're in my hand. So this is a combination. We're going to say from 5, we're choosing 52. And this number is going to be large. Let me, we'll do this real quick, right? This is going to be a very big number because you can even just start thinking about it, right? There are a lot of options here. I wrote that backwards, I realized. This should be from 52, right? We're from 52, choose 5. From 52, choose 5. So sorry about that. From 52, choose 5. The bigger number should always go first. There are 2,598,960 possible 5-card hands that I can have, right? Just right off the top deck. So I want 4 of those, right? I have the possibility of needing 4 of those. So what is the probability that I draw 5 cards, and they are unquestionably the 5 cards I need for the royal flush? So 4 out of my 2.5 million, I get, my calculator displays it as scientific notation. So this is what I have on my calculator, times 10 to the negative 6th. So for you keeping track at home, that's 1, 2, 3, 4, 5, 1, 5, 4. And even now, percent doesn't seem all too helpful, but just to represent it, that would be 0.1231554%. Right, chance of me just first 5 cards, royal flush, which is why in poker, in the casino, right, a royal flush is the big winner, the biggest payout, because it is the hardest one, undoubtedly, to get. So that's probability in its most basic sense. if I take this up to mutually exclusive events, ands and ors, I start to get a little bit interesting, right? I don't care just so much about just rolling the 5. Maybe I need to roll a 5 and flip a coin, or roll a 5 or roll a 6. Well, so the first thing I want to see here is mutually exclusive events. And we say that two events, A and B, so just whatever these events are mutually exclusive if A and B have no outcomes in common. Right, so this might be something like I roll a die, and I say I want to roll a 2 or a 5. Well, I can't do this in the same roll. If I have one die and I roll it, I can't have the die land on 2 and 5 in the same roll. That doesn't make sense, right? It's ridiculous. But something like, so this is, that's the eraser, that's why it's not writing. This is mutually exclusive. But something like drawing a card might not be, right? If I draw a card and I want to draw a jack or a heart, well, this is not mutually exclusive. Why? Because there is a jack of hearts in the deck. So this brings me to my and or statements here. So if I want the probability of one event or another, and another way we might write this is actually with set notation, and I would say the union of two sample spaces. It means the same thing, just a notational difference. I'm going to add, right? So it's the probability of A plus the probability of B. But my or implies but not both. So I need to eliminate the odds of both of those happening. So probability of A plus the probability of B minus the probability of A and B. So how do I figure that out? Sometimes you might be able to count if it's a relatively simple case, but I'm going to tell you that now. Probability of A and B, I'm just going to multiply the probability of A times the probability of B. And sometimes you might see this notated as A intersect B, again, kind of going to our set theory notation. You might see both. Just know how these are related. So let's try some examples here, some small examples here. Drawing a 4 or a heart from a deck of cards. So, or, right, I have my or statement here. Is this mutually exclusive? No, it is not. Why? Because there is a 4 of hearts in the deck. So my probability of a 4 or a heart, I actually now have to consider the probability of drawing the 4 of hearts. Right, so my probability of drawing a 4, there are 4 4s in the deck, right? One for each suit, so 4 out of 52. Let me just move this down here. Just a little more room. There are 13 cards in each suit, so 13 out of 52. But there is one 4 of hearts in the deck. There's one place where we say that these events overlap, they intersect, right? There's one case that satisfies both conditions. And for now, I don't care about it. So I'm just going to add all these together. 4 plus 13 is 17, minus 1 is 16 out of 52. And if I divide, I get 0.308. And again, if you prefer to see this as a percentage, that's 30.8%. We just move the decimal 2 places. All right, so same idea, rolling a 4 or a 6. Are these mutually exclusive? Yes, they are. Right, there is no way I could possibly roll one die and have it land on 4 and 6 at the same time. Well, what does that mean? That means the probability of A and B happening is 0 if it's mutually exclusive. So in this case, I can just add my two probabilities, right? probability of a 4 or a 6. And I'll show that one more time. I'll write this out kind of long form first. Right, there's no way at all that I could possibly get that, right? So that's 0. So I can effectively forget about it because these are mutually exclusive events, right? So that means my probability of both happening is 0. So how many ways can I get a 4? There is one way on a die to get a 4. There's one way on a die to get a 6. So my probability is 2 out of 6, or 1/3, which is 0.3 repeating. Again, if you prefer to see this as a percent, I would write it this way. Those are my OR statements. If I look at my AND statements, rolling a 2 3 times on a 6-sided die. I prefer to actually set this one up this way. Probability of 3 2s. And actually set up blanks so I can calculate each probability on its own. So I roll a die. And sounds like I'm losing my train of thought. I roll a 2. So there's 1 out of 6 ways I can get a 2. The rolls don't impact each other, right? If I roll the die once and I pick it up and roll it again, or even if I want to really be good about this and I roll one die, I pick up a new one, I roll that one, their rolls do not impact each other, right? We call things like that, maybe I'll use a different color here, right? We call rolls like this independent, where the events don't influence each other. So I can pick up my dice again, my die again, and roll it, and there's still a 1 out of 6 chance I get a 2, and likewise with my third roll. So this is an AND statement. I want to get a 2 and a 2 and a 2. So 1 over 216. Whoops, 1 over 216. So as a proportion, that's 0.0046. And as a percent, if you prefer, 0.46%. All right, well, what about non-independent, dependent events, you might say? What happens if I draw 5 cards, I have them all hearts from a deck of cards, and I'm going to put the extra restriction on here that I'm not replacing the cards. I'm not putting them back in the deck, right? So I can look at it 2 different ways. I could replace the cards. I can put them back into the deck every time. So there's always 52 cards in the deck when I draw. Or I can consider leaving them off on the side and seeing how my probability changes there, which is what I'm going to do here. Because I'm not replacing the deck, or the cards, then my events are dependent, right? The probability depends on the one I picked before. So the probability of getting 5 hearts, I like to set up my blanks. I just think it's easier to stay organized that way. I want my probability of getting a heart the first time. There are 13 hearts in the deck. There are 52 cards total. Assume I draw a heart. I'll take it and put it off on the side. So we're going to assume that this was a heart. I did good. So now there are 12 hearts left in the deck, and there are 51 cards left to choose from because I set that first card aside. Likewise here, right? 11 cards left in the deck, hearts left in the deck, 50 cards left in the deck. 10 hearts, 49 cards. 9 hearts, 48 cards. This is an AND statement, so I'm going to still multiply everything together. So in the numerator, I get 154,440. And in the denominator, I get, that's not right, 52 times 51 times 50, 48. I'm going to get 3,118,752,000. So 311,875,200. So if I take these 2 numbers and divide them, I get some more scientific notation. So I got 1, 2, 3, 4, 9, 5, And if you want to see this as a decimal, sorry, as a percent, 0.0495%. By the way, just kind of talking about our casinos again, right? All hearts, right? I have all the same suit. We call this a flush in poker. This is also a pretty high-ranking hand because, as you can see, it's not easy to get one. It's easier than a royal flush because you have other different ways you can get a heart, but it's still not easy. So that's what we're looking at here, right? So and and or events. Right, the last thing we're going to talk about is that sometimes it's easier to calculate the odds of your event not happening and use it that way instead. Depending on the thing I give you, it might be easier to think about what happens when the event is not going to occur. So the complement of an event A, that's our word here, is complement. The complement of an event A, we denote it this way, with a little apostrophe, and we call this A prime, is the set of all outcomes that does not include A. So if I let A stand for rolling a 6, then A prime would mean not rolling a 6. Right? All this really means is not A. So what does this mean for us? Well, the practical bit of this is to say that the probability of A prime is 1 minus the probability of A. Right? Something can either occur or not occur, but my probability must equal 1, then this is how I would look at it, right? If the probability of not rolling a 6, if I stick with that, right? Well, if we did this the long way, I could roll a 1, a 2, a 3, a 4, or a 5, right? I have 5 options out of 6. And I have one way out of 6 I could roll a 6. Well, sure enough, 1 minus 1/6 is 5/6. Right, so that's kind of my big formula in action here, right here. So, for example, drawing a card and having it not be a spade. I could do this long form. I could do this the long way out, but that's not always the most helpful. I could think about all the possible ways I could not get a spade, or I could say the probability of not a spade is equal to 1 minus the probability of having it be a spade. So there are 13 cards out of 52 in the deck. So 1 minus 13, 52 minus 13 is 39 out of 52, which should just be, yep, 75%. So that's all this is saying, is if sometimes you have a more complicated idea, complicated event, it might be easier to look the other way instead.